Let's get started today's course, today's class course. So, in the previous class, we learned about the data forwarding unit, right? Uh, Actually, in order to improve the performance of pipeline architecture, so this CPU requires a data forwarding unit and also data forwarding path, right? So this data forwarding unit and data forwarding path supports the data forwarding of instructions. And then, so in order to support this data forwarding, uh, we need a multiplexer and then the control unit, right? And then control unit generate the selection signal for multiplexers, right? So we learned about the conditions for data forwarding, right? Actually, we learned how to generate these control signals for the data forwarding multiplexers, right? And then, so in this class, we learned about the hazard detection unit, okay? So as I mentioned, we cannot avoid the waste of a clock cycle by the load use data hazard, right? So it is because when the load instruction is executed, the load instruction generate the result in memory stage, right? But this result is required in the EX stage by ALU. So cannot use. So because the load instruction will generate this result later than the EXTG in the next instruction. So the next instruction need to be delayed by one cycle. So, so our pipeline architecture, our pipeline CPU needs to support this operation. So it's a data hazard. So in order to support the data hazard, so we also require hazard detection unit, okay, like the data forwarding unit, right? So and then the approach is the same. So firstly, we define the conditions for enabling data forwarding, right? So this is the same. So actually, when we design the hazard detection unit, then firstly, we think about the conditions. So condition means that how can we detect this load use data hazard cases, right? So what is the condition? So firstly, so I mentioned this is the load use data hazard, right? So obviously, why it doesn't work? So obviously, the previous instruction is load instruction, right? So then how can we detect the load instruction? So actually, our control unit, the main control unit, check the opcode field of an instruction, right? And then if an instruction is a load instruction, right? Then we generate the mem read signal, right? Mem read signal. So which means when a mem read signal is 1 by the main control unit, then we can know that, oh, this is the load instruction, right? So we can detect this load instruction. And also, then what is the other conditions? So load use data hazard looks like this. So load word and X1. X1 is the destination register of load word, right? What? And then the following instruction use, what happened? This loading, this destination instruction, no, destination register of load instruction, right? So actually the condition is very similar to the the data forwarding condition. So in order to support the data forwarding, we compare the 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 register number of the destination register of the former instruction and the register number of source registers of the following instructions, right? So that was the data forwarding condition. So in this case, we can just compares the destination register number of former instruction, right? And then but the former instruction needs to be load instruction, and then we just compare the source registers of following instructions. Then when the following instruction is stalled, so when do we need to detect this load use data hazard cases? So this is the pipelining. Why? I think my stylus is not working well. So this is the load instruction, and okay, I don't know why. So this is the load instruction, and then this is some other instruction, following instruction. So let us assume that the following instruction requires data from the load instruction, right? So it's a load word. Okay. So we can detect this load use data hazard when the load instruction is in the EX stage, right? So I don't know why, because my pen is not working well. And then the following add instruction is in the ID stage, right? Because in the ID stage, we can figure out the destination register number of the following instruction, and then also we can detect this load instruction. Okay, so when the add instruction is in the ID stage, and then we can detect this load use data hazard case, and then this add instruction will be stalled, will stay in ID stage for one cycle. So I explained about the pipeline stall. So pipeline stall means that the instruction stays, right? So actually for the normal cases, the instruction needs to be propagated to the next stage in the pipeline architecture, right? But in the pipeline stall case, an instruction is stalled, okay? It means an instruction stays in a certain pipeline stage for one cycle. So in this case, we just assume that only one cycle is wasted, but in the real hardware, real CPU, the several cycles can be also wasted, okay? But also, so you can just understand that pipeline stall means that, instruction stays in a certain stage, right? I don't know why. Okay, so this is the pipeline stall. Then what will happen? So add instruction will stay in ID stage, and then load instruction will be propagated to the memory stage. Then we can get the result by this load instruction from the data memory, right? Then how can you handle the instruction in EX stage? So load word is here, and load word is here, and then so it's memory stage, and then load word is here, and then add instruction is in the ID stage. Then what will happen in the EX stage? So actually, in the pipeline stall concept, so conceptually, we learn, where is this one? Okay. So when the so we learned that when the this load use data hazard is detected, then we just learned that one cycle is wasted. So which means the this add instruction, the following instruction is replaced with the bubble, right? Bubble. What does that mean? So bubble means it's no operation. So pipeline CPU does nothing. It's no operation, right? So add instruction stays in ID stage, then but the EX stage, then how about the EX stage? EX stage doesn't EX stage does not receive any instruction. So what does that mean? It means the instruction in EX stage is the becomes the no operation. Okay, because it does nothing. It does nothing, right? So how can we make the no operation? So if we just make all control signals zeros, right? Then the instruction will do nothing. It's no operation. So we can generate the no operation like this. Okay. So we make all control signals zeros, right? So this figure explains the scenario, right? So this is the load instruction, and then the following add instruction received data from the load instruction, right? So this is the load use data hazard case. So we need to make this end instruction stored in the ID stage, right? Then this end instruction can receive data from the load instruction by data forwarding from the this write back stage, right? So when the load instruction is in the uh, load instruction in the EX stage, and then actually the end instruction is fetched. Okay, so no. Okay, let's start from the CC1. The load instruction is fetched in at CC1, the clock cycle number 1, and then at CC2, the load instruction is in the ID stage. And actually, the end instruction is also fetched, right? So we need to fetch the instruction. The fetch is always performed, right? Then when the load instruction is in the EX stage, then this end instruction is in the ID stage. So when the load instruction is in the EX stage, then we just check the load use data hazard case, right? So as I mentioned, so end instruction needs to be stored in the ID stage. Will stay in ID stage. So when this end instruction is in the ID stage, we check the data hazard, right? Load use data hazard. When the load instruction is in the EX stage. So when this data hazard is detected, end stays in this ID stage, but load instruction is propagated to the memory stage, right? And then in the EX stage, so load instruction is in the memory stage, so load is here. And then in the EX stage, we need to generate the NOP. It's a bubble. It is represented as a bubble, right? It's NOP. And then the end instruction is still in the ID stage, right? So the load use data hazard works like this. And then load instruction will fetch data from this data memory. Then when the end instruction is in the EX stage, then this data can be forwarded. Okay, forwarded from this write back stage, right? So that's how the load use data hazard is handled in this 5-stage pipeline architecture. Okay, so the required operation, firstly, we need to detect this load use data hazard case. And then if the load use data hazard is detected, then the end instruction. And the instruction stays in ID stage, right? And then load instruction is propagated, and we just generate the bubble. And then I explained that we can generate the bubble by making all control signals 0, right? Then how about the following OR instruction? So when the end instruction is actually in the ID stage, then OR instruction, the next instruction, OR instruction is in the instruction fetch stage, right? So what does that mean? OR stays in ID stage. So, no. End instruction, so sorry about that. And stays in ID stage. Then how about the OR? The OR instruction cannot be propagated to the next stage because ID stage is already occupied by this end instruction, and then end instruction stays in ID stage, right? So it means this OR instruction also need to stay in instruction fetch stage, right? So how can you implement this? The instruction, so OR instruction stays in instruction fetch stage. If we do not update the program counter, right, then OR instruction stays in instruction fetch stage. Do you understand? So in the instruction fetch stage, we fetch instruction from instruction memory using program counter value. But if this program counter value is not changed, right, then the same instruction is in the instruction fetch stage. So in order to make this OR instruction stay in the instruction fetch stage, we 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 can just do we do not update the program counter value, right? So by doing this, we can make this OR instruction stay in the instruction fetch stage. Also, this OR, we just disable the update of the pipeline register, right? So by doing this, this OR instruction is not propagated to the next stage. So what is required? We disable the update of pipeline register. Okay, and then this end instruction stays in the ID stage, and then we can just make the new NOP operation. So this is the required operation for the load use data hazard case. Okay. So firstly, let's see the condition. Oh, my table condition is not good. Okay. So like the data forwarding, so as I mentioned, so we can just check the RD, the destination register in EX stage because the load instruction is in the EX stage. So we just use the destination register in EX stage. So it means it is the output of ID/EX pipeline register, right? So this means the RD in EX stage. Okay, and then the following instruction is in the ID stage. So we just use the RS1 and RS2 in ID stage, right? So we compares the RD and RS1 or RD and RS2. And then the instruction in the EX stage is the load instruction. It's a memory read. So in this case, so we can detect the load use data hazard. Then if detect, store and insert bubble. Okay. So and then as I explained, we can make the NOP operations, the bubble, so by making all control signals 0. Okay. Then also we disable the update of the program counter and instruction fetch and ID pipeline register, right? Instruction fetch slash ID pipeline register. Okay. So by doing this, we can make the instructions stored in the ID stage. So this is the architecture. So architecture of the data, no hazard detection unit. Okay. So as you can see, the hazard detection unit is in the ID stage. So it is because and we just apply this hazard detection in the following instruction is in the ID stage, right? And then as you can see, hazard detection unit just compares the RS1 and RS2 in the ID. And then where is the okay? So this line. So this line. So the RD. So we just compare the RS1 and RS2 in ID with the RD in EX stage, because as you can see, the RD is delivered from the EX stage, right? And then also memory read signal is required. So the the load instruction is in the EX stage. So we can check the memory read. So hazard detection unit just to detect the load use data hazard. And then you can also observe the output control signal from this hazard detection unit, right? So as you can see, hazard detection unit generate the PC write signal and then instruction fetch slash ID write signal, okay? And then it also generate this control signal. So PC write signal. So which means if the PC write is 1, then the PC is updated. So if the hazard is detected, the load use data hazard is detected, then PC write becomes 0. So PC is not updated. The program counter is not updated. So by doing this, the instruction in instruction fetch stage will stay in the instruction fetch stage, right? And also, this hazard detection unit generates the pipeline register write update signal. So instruction fetch slash ID pipeline register write signal. So normally this is 1 because if this the pipeline, it means that this pipeline register update is enabled. But when the hazard is detected, this signal becomes 0, right? Then it is not updated. So the instruction is not propagated to the next stage. So instructions in instruction fetch and ID stage are maintained. just stored in these two stages, right? So stay in these stages. Also, when the hazard is detected, the hazard detection unit generates this signal, right? And then, as you can see, it makes all control signals 0, right? So it generates the bubble in the next cycle, okay? So this is the hazard detection unit. So, so, like the data forwarding unit, so this part can be a little bit tricky because so this is also the corner case, the corner cases, one of the corner cases of the pipeline architecture, right? So we need to detect, firstly, we need to detect the load user data hazard, and we need to control the pipelining of the CPU architecture, right? So this is the corner case. So in order to support this operation, so I I firstly explained about the condition, the detection condition, and then when this condition is detected, then we need to perform the appropriate operations in the pipeline architecture. So I also explained the required operation. Okay. So and then in order to understand this operation, then you can also check the input and output signals of this control unit, like hazard detection unit. Okay. And then, so this hazard detection unit receives the required signals like the the source registers and destination register and the memory read control signal. And then it generates these control signals, okay? The PC write, also the pipeline register write, and then the it also makes the all control signals 0, okay? So you can understand the operation of this pipeline architecture, not hazard detection like this, okay? So the, you know, when the load use hazard is detected, one cycle is wasted, right? Because uh, when the load use data hazard is detected, then the instructions stay in instruction fetch and ID stage, and then we just make bubble. There's no operation in the EX stage. So this bubble occupies the one cycle, right? So one cycle will be wasted, right? So actually we learned already covers this. So using the compiler techniques, then we can adjust the order of instructions. So by doing this, we can avoid the load use data hazard, right? But you can also you, but as you can see, these instructions are in the basic blocks, right? So in chapter 2, so we learned about the basic block, right? And then I mentioned that actually the basic block is very important actually for the compiler techniques, right? So it is because inside of the basic block, and then if we just maintain the data dependencies, then we can adjust the order of instructions, right? So it means a compiler can apply the optimization techniques inside of this basic block, right? So as you can see, this is the basic block. Okay. There is no target of branch instruction. Also, there is no branch instruction, right? So we can adjust the order of instruction, but we need to maintain the data dependencies. So obviously, right? So if the data dependencies are broken, then this code will generate the incorrect result, obviously, right? So by adjusting the order of instructions, so we can avoid the data hazard, right? So if there are some in the unrelated instructions between the load and the following instructions, we can avoid the data hazard, right? So this is the compiler technique. Okay, so we learned about the data hazard. Okay, and then so this data hazard is a the performance overhead. Performance overhead. 이거 좀 해줄래? Okay, so okay, now so let's learn about the control hazard. So this is the another critical the hazard, right? Then let's see why control hazard happens in the pipeline architecture. So okay. Uh, then let's see why control hazard are causes in the pipeline architecture. So as I mentioned, the control hazard are caused by control instructions. And then what are control instructions? Control instructions are branch instructions, jump instructions, and also exceptions, right? So then why the clock cycles can be wasted because of control instructions. So the control instructions update program counter, right? And then the program counter is we use the program counter value in the instruction fetch stage, right? But if this update is delayed, right, then the clock cycles can be wasted, right? That's why the control hazard are can happen in the pipeline architecture. So this is the example. So as you can see, this is the BQ instruction. So this is the branch instruction, right? So at clock cycle number 1, the branch instruction is fetched, and then at clock cycle number 2, branch instruction is in the instruction decoding stage, ID stage, and then next instruction is in the instruction fetch stage. So you may think that, branch instruction does not update the PC yet, right? We don't know. So we don't know the result of this branch instruction, right? So what is the result of a branch instruction? It's true or false, right? But actually, when the branch instruction is in the ID stage, we don't know. We don't know the result of this branch instruction. So we just assume that the branch is not taken, right? So the next instruction is fetched, the next instruction, okay? And then the branch instruction is in the EX stage at clock cycle number 3. And then, so actually the XO, so so when the branch instruction is in the EX stage, X1 is compared with the X2, right? Using the ALU. But the ALU exhibits some delays, right? We don't know the result of this comparison immediately, right? This is hardware. So when the comparison is being performed, also the next instruction is fetched, right? So here and here. And then we can get the result of comparison at the late part of the clock period. So actually, this result is also propagated to the next stage. It's a memory stage, right? So branches here, branches in the memory stage. Oh, we can get now finally we know the result of branch instruction. And let us assume that this result is true. So what does that mean? We need to jump to the target of branch instruction. But we finally get to know the result of branch instruction in memory stage. So what does that mean? Using this result, we just generate the PC update signal. So PC will be updated by the target of branch instruction, right? But this is the pipeline architecture. So this update will be reflected in the next stage, right? Do you understand? So when the branch instruction is in the memory stage, actually the new instruction is already fetched, right? So this update signal, this PC update by branch instruction, this updates will be reflected in the next cycle. So this is the pipeline architecture. Okay, so, and then it works with the clock signals, sampled by clock signals, right? So using the result of a branch instruction and then using the target of a branch instruction, new instruction, the target instruction will be fetched at clock cycle 5, right? Then how about the DJ instruction? Actually, this is the correct instruction, right? This load instruction is the correct instruction because we finally get the result of branch instruction in the memory stage. And then we know that we get to know that the result is true, right? So these instructions are incorrect instructions. Incorrect instructions, right? So we need to cancel the execution of these instructions, right? How can we cancel? So we can just make these instructions nope. Okay, we just change these instructions to nope with the same way. We just make all control signals of these instructions 0, right? So these instructions are all flushed. It's cancelled. So So it's called the pipe flushy because what is the flushing? So flush means so in a toilet. So when we after so we can just push the flush button and then the toilet our flushed, right? So uh the instructions, the incorrectly fetched or incorrectly executed, incorrectly decoded instructions are all flushed from the pipeline. Okay, so then what's the problem? Problem is that we just waste 3 cycles. So in this example, 3 instructions are flushed. So when the branch instruction is true, when the condition of the branch instruction is true, then 3 cycles are wasted. So this is the control hazard. So cycles are wasted. This is the control hazard. Then how can we reduce the performance impacts from this control hazard? So what is the problem actually? What is the problem of this control hazard? Why? Why 3 cycles are wasted? What's the problem? Is it because we get to know the result of branch instructions late, right? Because we finally get to know the result of a branch instructions when the branch instruction is in the memory stage. So problem is that, if the condition is true, then the following instructions are in the instruction fetch, ID, and then EX stages, right? These instructions need to be flushed, right? Then what is required? So how can we improve? So it means how can we reduce the wasted clock cycles by this branch instruction? If the condition of branch instruction is detected earlier, right? So problem is that so when we get to know the result of branch instruction when the branch instruction is in the memory stage. But if we can detect this result earlier, for example, in the ID stage, then we can reduce the number of wasted clock cycles. Right, obviously, right? So do you understand? So by doing this, we can reduce the performance overhead. So performance overhead means that it's the some performance performance degradation by some impacts, right? So if we detect the result of a branch instruction earlier, then we can reduce the performance overhead by this branch instruction. Okay, so that's how we can handle the control hazard of a branch instruction. Okay, so you need to understand this. Okay, then so this slide also explains the wasted clock cycles by branch instructions. Okay, so actually when you read the textbook proposed the solution that so we can detect the result of this BQ just after the register file. So this is the textbook's solution, right? So what is the benefit? The benefit means that, as I mentioned, we can get to know the result of branch instructions when the branch instruction is in the ID stage. So you may think that, but for this comparison, then we can observe some delays, right? So it's true, right? But actually, in the text, in this, our CPU just supports BQ instruction, right? And then in order to know the result of BQ instructions, then we can just check the equality of each bit, right? So how can you check the equality of the 2 bits? We can use the exclusive OR gate, right? Because the exclusive OR gate. So 0, 0, it's 0, 0, 1 is 1, and then 1, 0. My stylus is 1, 0, 1, 1, 1, 0. So this is the output of the exclusive OR gate. So in the exclusive OR gate, the two bits are different. The output is 1. I don't know why. If tell us wait. 1. So using the exclusive, so by applying exclusive OR gate for each bit, and if we detect the ones, then we can detect the inequality of two data, right? So, the exclusive OR gate is much faster than subtractor, right? So we can compare the equality of each bit in parallel, and then we can just apply the large OR gate. Okay, so by doing this, we can quickly get the result of BQ, right? So the textbook solution, so in order to reduce the performance overhead by branch instruction, the textbook solution is to add the dedicated comparison unit, the dedicated equality check unit just after the register file, right? So by doing this, we can just detect the result of a branch instruction. Actually the result of BQ more quickly. Okay. So using the textbook solution, we can detect the result of branch instruction in the ID stage. So which means when the branch instruction is in the EX stage, then the target of a branch instruction can be fetched. Okay. So only one cycle will be wasted by this branch instruction. So by doing this, we can reduce the performance overhead by the branch instruction. So actually, this is some basic approach. So I mentioned that because the branch is detected late, we waste more cycles, right? Many cycles. In order to reduce this number of wasted cycles, we need to detect branch instructions earlier, right? So textbook solution is to add dedicated comparison unit after the register file. But this solution also includes some problems. Why? What? What are problems? Actually, other branch instructions such as BLT or BGE, for BLT and BGE, we cannot use this solution, right? In order to get the result of this BLT and BGE, we need to perform subtraction, right? We just compare the magnitude of two numbers using BLT and BGE. So actually, this solution can be applied to the BGE. No, BQ and BNE, right? And then another problem. So actually, I don't like the textbook solution. Another problem is that this solution causes another data hazard. So what's the problem? So, in order to handle data hazard by the arithmetic and logical instructions, we added the data coding multiplexers in the EX stage, right? But as you can see, in the using this solution, the BQ, the result of BQ is detected in the ID stage. So what does that mean? So like this case, add x1 and then some values because my stylus is not good. So BQ and then BQ use the x1, x2 like this. Then what's the problem? The destination of this add instruction is used by the two source registers, one of two source registers of the next BQ instruction. So in this case, if the BQ is performed, so comparison is performed in the EX stage, then the BQ can receive the forwarded data after this forwarding multiplexers. Do you understand? But in this solution, the BQ compares these two values in the ID stage. So this BQ cannot receive data from these forwarding multiplexers. Do you understand? So new data hazard. New data hazard are caused by this solution. Okay? Because the BQ cannot receive data from forwarding multiplexers because the BQ is performed in the ID stage. So in this case, then actually we need to delay the execution of BQ. So which means the BQ stays in the ID stage until this register value is internally forwarded in the register file, right? So it causes additional data hazard. Okay. So this is the problem. Okay. So okay. So usually this slide explains this new data hazard. Okay. Okay. So actually, so I think that this design is better. So it means actually we can make the dedicated branch unit just after the forwarding multiplexers. Okay, so in this architecture, so you can find that the branch is compared in the EX stage, but branch instructions do not use ALU because the ALU needs to support the various types of operations. So that means the ALU will exhibit the very long delay. But if we just use the dedicated branch unit, okay, then and this dedicated branch unit can get the result from these forwarding multiplexers, and then but this branch unit is separated from the ALU, right? Then we can get the result of branch instruction slight more quickly than the ALU because this is the dedicated unit. Then this result is updated to the PC. So in this case, the branch, we can know the result of a branch instruction in the EX stage, when the branch instruction is in the EX stage, and the target of a branch instruction is reflected when the branch instruction is in the memory stage. Okay? Okay, do you understand? So by doing this, so we can just reduce the one cycle. But this solution does not cause the new type of data hazard. So actually this is more complex, and then also the problem is that the clock cycles can be wasted more because of new data hazard. So as I mentioned, when you use this this hardware architecture, then actually the branch can receive the forwarded data by internal forwarding in register file, right? So which means the branch instruction needs to wait many cycles. So using this structure, so we can reduce the some we can quickly detect the branch instruction, but this this structure causes the new data hazard. So actually we can think that the performance improvement is not uh, large. Okay. So anyway, so actually I like this structure better because and then so which means we can use the dedicated branch unit in the EX stage. So the if the branch is taken, so which means the branch is true, then the penalty is the 2 cycles. Those 2 cycles are wasted. The branch is not taken, so no penalty. Okay. So actually, so we will have the one more lab assignment. Actually, in this the last lab assignment, so you will be requested to design the pipeline architecture, right? So actually, this is the some tricky parts of the pipeline architecture. Actually, as I mentioned, the concept is not difficult. So we can just split the single cycle processor architecture into the 5 stages. Okay, but the tricky part is the data forwarding unit, and then the data hazard detection, also the branch control, the control hazard, how to handle the control hazard. Okay. So in the lab assignment, I just used this architecture, not this architecture, because this architecture is more difficult. Okay. So we need to handle the new data hazard for this architecture actually. So actually for the last lab assignment, we will be requested to implement this pipeline architecture. Okay, so which means the branch instruction is detected in the EX stage, right? So actually, but even though we use this architecture, if the branch is taken, then 2 cycles are wasted. So you may think that this performance avoid is small, but actually it's not because we frequently use branch instructions, right? So actually the branch instructions usually occupies the 20% of all instructions, right? So we frequently use the branch instructions. So for example, for loop, okay? If we use the for loop, and then usually the branch instruction is located in the end of the for loop, then if this for loop is, we frequently use this for iteration for loop for the repeated operations, right? So which means this branch instruction is taken multiple times. So which means clock cycles are wasted multiple times. Okay. And then this performance overhead is not small. So actually, branch instruction is very critical in the CPU performance, right? So, uh, so if you learned about some advanced computer architecture, then you can learn that. Actually, you can learn the advanced architecture. So actually, so as I mentioned, the modern CPU architectures use a different type of pipelines. Okay, it's called out of order processing. So actually, using this out of order processing architecture, we can handle data hazard effectively. But problem is control hazard. The control hazard are actually caused by branch instructions, right? So PC is updated late. So we cannot handle the branch instructions, the control hazard by branch instructions effectively in the modern architecture. So we need to use the actually new technique. Okay. So and then anyway, in the CPU, the performance of CPU is significantly degraded by branch instructions. That's very critical. Okay. So you may think that, oh, this is just the two cycles of penalty, but it's not actually. So actually, even though this is the two cycles of penalty, but the performance is degraded large. So think about this. So performance is degraded by 40% or 30%. It's huge actually, right? So how can you reduce the performance overhead further? We can apply the branch prediction. So what is the purpose of branch prediction? What is the problem of branch instructions? So why many cycles are wasted? Because the result of branch instruction is detected late. This is the problem. If the branch instruction result is detected late, then more cycles will be wasted. Okay, but we cannot detect the result of branch instruction earlier. Okay, because so we actually the two operands are need to be two operands are compared by branch instructions, right? So then what's the possible solution? Prediction. And then this is the dynamic prediction. So dynamic means that so we predict the result of branch instructions in runtime. So it means when a code is executed in CPU, then we can just predict the result of instruction. So in a computer architecture, so we frequently use the static and dynamic. 뭐가 문제예요, 이거? So static means the result. The result is already determined before execution, right? So actually the compilers also can analyze some behavior of instructions, and compiler can give some hints to the CPU. So this technique is called the static technique. Also, the compile optimization is some static techniques. But CPU can monitor the behavior of instructions in runtime. So while the instructions are being executed, then the CPUs can predict the behavior of some instructions. So this technique is called the dynamic technique. Okay. So what does that mean? So dynamic prediction. Dynamic prediction means that CPU predict the result of branch instructions in runtime. Okay. While the instructions are being executed, the CPU predict the result. And then actually this technique is very important, very critical in CPU architecture, right? Then what is branch prediction? So obviously branch prediction means that we predict the result of a branch instruction. So what is the result of a branch instruction? The result is true or false, right? So like as you can see, BQ, X1, X2, Actually, the result is true or false, right? So prediction means we can predict the so we can predict the result of this branch instruction before the branch is executed. Then how? So how can we predict the future event? I mentioned that prediction means that a CPU estimate or predict the result of a branch instruction before the branch is executed, right? Then how can we predict the future event in the real world? So for example, so in sports, so how can you predict the result of the sports game? It just monitors the history, right? The past events of the sports game, right? So we analyze the performance of the, for example, in the baseball, pitchers or batters, but these are history, the past events, right? And then based on this history, then we can predict the future result, right? It's the same. It's the same to the CPU design. So branch result can be also predicted. How? We can monitor the previous result of branch instructions. So for example, so let us assume that this is the for loop, and then this for loop is the I equals 0, and then I is less than 100. So I is less than 100. I don't know why. My stylus is not good. 뭔가 고장난 것 같아요. Then this loop will be repeated 100 times, right? Again and again. So which means the branch is taken 100 times. So what does it mean? If we just detect, oh, this is the same branch instruction like BQ. So there is this BQ, and then the BQ is taken, right? And then oh, in the next, then we can assume that this BQ will be taken again, right? So this is the prediction by monitoring the past events of this branch instruction. Then we can predict the result of branch instruction. But which means in order to predict the future result, we need to store the past events, right? So in the sports game, so in order to predict some future result, then we just store the every performance of pitchers or batters, right? This is the history. CPU is the same. In order to predict the result, then we need to store the result of past event. Then what is the result of a past event? So that is the result of branch instructions. So this is the one bit predictor. So one bit predictor means that. So actually, so as I mentioned, the result of branch is the true or false. So this is T, right? True or false. And then we can represent this result using one bit, right? Because it's a true or false. So one means true, and then 0 means false, right? So then one bit predictor means that we just store the one past event of this branch instruction, right? And then based on the past event, so if the result is 1, then it's true. Then we just predict that, oh, the next event is also 1. What happened? this is the one bit predictor. Okay. So it means for each branch instruction, we can just store one bit, the one bit of result. Okay. So, and then actually this is very simple. If the past event is true, then we just assume that the next event is also true. If the past event is false, then we can assume that the next event is also false. So this is the one bit predictor. So it will work well for this iterative loop. So for example, it's a 4I is less than 100. Then if the BQ is here, the end of the loop, then if the past event is true, it means it's taken, then it will be taken 100 times. Then we can predict the result of this branch instruction correctly for 99 times, right? It's very good. Out of 100, we can predict the result of a branch instruction 99 times correctly, okay? So, because we can use this prediction technique because the prediction rate is very high in the CPU, right? If the prediction rate is very low, we cannot use the prediction technology. But in CPU, the prediction rate is very high, so we can use this branch prediction. Okay, so this is the one bit predictor, and then okay, so I will stop here, and then also we will learn about the two bit predictor, and then some other techniques late in the next class. 네, 예, 감사합니다. 전자기기들이 좀 오늘 문제가 있어가지고.